In quantum field theory, the vacuum state is the quantum state with the lowest possible energy. Generally, it contains no physical particles. Zero-point field is sometimes used as a synonym for the vacuum state of an individual quantized field. It is a mistake to think of any physical vacuum as some absolutely empty void. According to quantum mechanics, the vacuum state is not truly empty, but instead contains fleeting electromagnetic waves and particles that pop into and out of existence. The QED vacuum of quantum electrodynamics was the first vacuum of quantum field theory to be developed. QED originated in the 1930s, and in the late 1940s and early 1950s it was reformulated by Feynman, Tomonaga and Schwinger, who jointly received the Nobel Prize for this work in 1965. Today the electromagnetic interactions and the weak interactions are unified in the theory of the electro-weak interaction. The Standard Model is a generalization of the QED work to include all the known elementary particles and their interactions. Quantum chromodynamics is the portion of the Standard Model that deals with strong interactions, and QCD vacuum is the vacuum of quantum chromodynamics. It is the object of study in the Large Hadron Collider and the relativistic heavy ion collider, and is related to the so-called vacuum structure of strong interactions. Non-zero expectation value. If the quantum field theory can be accurately described through perturbation theory, then the properties of the vacuum are analogous to the properties of the ground state of a quantum mechanical harmonic oscillator. In this case, the vacuum expectation value of any field operator vanishes. For quantum field theories in which perturbation theory breaks down at low energies, field operators may have non-vanishing vacuum expectation values, called condensates. In the Standard Model, the non-zero vacuum expectation value of the Higgs field, arising from spontaneous symmetry breaking, is the mechanism by which the other fields in the theory acquire mass, energy. In many situations, the vacuum state can be defined to have zero energy, although the actual situation is considerably more subtle. The vacuum state is associated with a zero-point energy, and this zero-point energy has measurable effects. In the laboratory, it may be detected as the Casimir effect. In physical cosmology, the energy of the cosmological vacuum appears as the cosmological constant. In fact, the energy of a cubic centimeter of empty space has been calculated figuratively to be 1/1,000,000th of an erg. An outstanding requirement imposed on a potential theory of everything is that the energy of the quantum vacuum state must explain the physically observed cosmological constant. Symmetry. For a relativistic field theory, the vacuum is Poincare invariant, which follows from Weitmann axioms but can be also proved directly without these axioms. Poincare invariance implies that only scalar combinations of field operators have non-vanishing VEVs. The VEV may break some of the internal symmetries of the Lagrangian of the field theory. In this case, the vacuum has less symmetry than the theory allows, and one says that spontaneous symmetry breaking has occurred. See Higgs mechanism, Standard Model. Electrical permittivity. In principle, quantum corrections to Maxwell's equations can cause the experimental electrical permittivity epsilon of the vacuum state to deviate from the defined scalar value epsilon 0 of the electric constant. These theoretical developments are described, for example, in Dietrich and GIEs. In particular, the theory of quantum electrodynamics predicts that the QED vacuum should exhibit nonlinear effects that will make it behave like a birefringent material with epsilon slightly greater than epsilon 0 for extremely strong electric fields. Explanations for dichroism from particle physics outside quantum electrodynamics also have been proposed. Active attempts to measure such effects have been unsuccessful so far. Notations. The vacuum state is written as or. The vacuum expectation value of any field phi should be written as virtual particles. The presence of virtual particles can be rigorously based upon the non-commutation of the quantized electromagnetic fields. Non-commutation means that although the average values of the fields vanish in a quantum vacuum, their variances do not. The term vacuum fluctuations refers to the variance of the field strength in the minimal energy state, and is described picturesquely as evidence of virtual particles. It is sometimes attempted to provide an intuitive picture of virtual particles based upon the Heisenberg energy-time uncertainty principle, arguing along the lines that the short lifetime of virtual particles allows the borrowing of large energies from the vacuum and thus permits particle generation for short times. Although the phenomenon of virtual particles is accepted, this interpretation of the energy-time uncertainty relation is not universal. One issue is the use of an uncertainty relation limiting measurement accuracy as though a time uncertainty delta t determines a budget for borrowing energy delta E. Another issue is the meaning of time in this relation, because energy and time do not satisfy a canonical commutation relation. Various schemes have been advanced to construct an observable that has some kind of time interpretation, and yet does satisfy a canonical commutation relation with energy. The very many approaches to the energy-time uncertainty principle are a long and continuing subject. Physical nature of the quantum vacuum. According to Astrid Lambrecht, when one empties out a space of all matter and lowers the temperature to absolute zero, one produces in a Gedanken experiment the quantum vacuum state. According to Fowler and Guggenheim, the third law of thermodynamics may be precisely enunciated as follows. It is impossible by any procedure, no matter how idealized, to reduce any assembly to the absolute zero in a finite number of operations. Photon-photon interaction can occur only through interaction with the vacuum state of some other field, for example through the Dirac electron-positron vacuum field. This is associated with the concept of vacuum polarization. According to Miloni, all quantum fields have zero-point energies and vacuum fluctuations. This means that there is a component of the quantum vacuum respectively for each component field, such as the electromagnetic field, the Dirac electron-positron field, and so on. According to Miloni, some of the effects attributed to the vacuum electromagnetic field can have several physical interpretations, some more conventional than others. The Casimir attraction between uncharged conductive plates is often proposed as an example of an effect of the vacuum electromagnetic field. Schwinger, Derrida, and Milton are cited by Miloni as validly, though unconventionally, explaining the Casimir effect with a model in which the vacuum is regarded as truly a state with all physical properties equal to zero. In this model, the observed phenomena are explained as the effects of the electron motions on the electromagnetic field, called the source field effect. Miloni writes, the basic idea here will be that the Casimir force may be derived from the source fields alone even in completely conventional QED. Miloni provides detailed argument that the measurable physical effects usually attributed to the vacuum electromagnetic field cannot be explained by that field alone, but require in addition a contribution from the self-energy of the electrons, or their radiation reaction. He writes, the radiation reaction and the vacuum fields are two aspects of the same thing when it comes to physical interpretations of various QED processes, including the Lamb shift, van der Waals forces, and Casimir effects. This point of view is also stated by Jaffe.